This video is an Azure Machine Learning Studio experiment walkthrough for a customer propensity prediction problem. It is intended to be used by those who have never used Azure Machine Learning Studio, or for those AML beginners looking for a simple reference for a project of their own. Before we begin, we should define what we mean by customer propensity. What we're trying to understand is a likelihood, or propensity, that a customer will buy our product or service so that we can tailor our sales or marketing processes for future customers. Propensity prediction is an example of a classification problem. We're putting customers into one of two categories, buy or won't buy. As there are only two classifiers, this type of problem is often called a binary classification problem or a two-class classification problem. The principles and techniques explained in this walkthrough apply to any similar kind of binary classification problem, for example, predicting customer churn or predicting whether a credit card transaction is fraudulent or not. So the purpose of this walkthrough is so that you understand the general method for developing a customer propensity predictive model and how to use AML and its extensive features to your advantage for the binary classification problems. This is by no means the only way to go about solving a customer propensity problem. Different people will have slightly different variations, but the underpinning method will be similar across the board. We're going to be using existing data that we hold about customers and whether they did or did not buy the specific product or service to develop and train an algorithm that can be used to predict the propensity of a sale for new customers in the future. Let's talk about the general method we work around when attacking a problem like this. Firstly, we define our hypothesis. This needs to be a statement which we can either prove or disprove. It is important to have some sort of measure of success so we know whether we have indeed proved or disproved the hypothesis. Next, we need to identify the data and really understand what it's telling us. We need to understand where it has come from, how reliable and accurate it is, and how the data is stored. We then manipulate the data and suitably prepare it for it to be incorporated into a machine learning model. This stage is more often than not the longest and most arduous of stages, but it is crucial to ensure good results. At this point, we consider the data we have in front of us and choose and apply different machine learning models. This is very much a trial and error stage, and it may take some time establishing which is the best model. Finally, we evaluate the results and compare these to our hypothesis to come to an overall conclusion, forming suitable recommendations for the relevant business stakeholders. Let's now take a look at our example. This example is based on an e-commerce business that is interested in changing its business processes to prioritize customers that are more likely to purchase their new service based on the information they provide at various stages throughout the purchasing workflow. So it is our job to try and find a trend in the data. This leads to our hypothesis. It is possible to predict which customers are likely to purchase a new service given the details we capture about them in our e-commerce system. The hypothesis will be considered to have been proved if a predictive model is able to predict propensity across a historical dataset provided with a 75% success rate. The 75% value is necessary so we have some sort of metric to aim for when evaluating the suitability of our model. It's important to note that rather than simply returning true or false, a predictive model will return a score between 0 and 1 for each record that it classifies. Deciding at which point a prediction counts as positive, i.e. the customer will buy the product, depends on the trade-offs between predicting false positives and false negatives for the specific scenario. For example, it may be more beneficial to be more confident of the positive values at the expense of making fewer positive predictions. We're going to use the area under curve metric to measure the success of our model. This value is particularly useful as it's the only metric which takes account of variations in this threshold between positive and negative values. We'll talk more about this later in the walkthrough when looking at results. Okay, now we have outlined our objective and defined our hypothesis, we can begin with the data analysis. So here I am on Azure Machine Learning Studio, and as you can see, we have all these icons on the left-hand side. The projects icon is where all your projects are stored, and if you create a project, in it you can store multiple experiments, notebooks, or datasets, etc., and it's all kept in one place. In this walkthrough, we are only looking at the experiment service that AML Studio offers, so there is no need to create a project. To create a new experiment, click New, Experiment, Blank Experiment. At the top of the page you'll see the title, and in this example we'll click on this and change it to Customer Propensity Walkthrough. So first things first, we need to locate our dataset. In this example, our data is a comma-separated value file, and we can view it here in Microsoft Excel. As you can see, there are multiple columns, each with corresponding data. This dataset is what has been collected from users of the website when they enter details about themselves. Okay, the first thing I should point out is that you shouldn't get worried when you see seemingly random numbers for a particular category. If we quickly sort the age range column, we see that we have the distinct values 0, 11, 13, 16, and 19. Now, this looks random, but in the source system where this dataset was drawn from, each of those values would correspond to a specific age range, probably selected in a drop-down list by the user. It's important to realize that it doesn't matter what the values are because they will be taken as categories during the experiment. All that matters is that there is only one value representing any given age range. Most of the titles are self-explanatory. We do not need to worry about the sales channel column because by the looks of it, it's empty. Let's just verify that by filtering the column and seeing what values it holds. So, as we thought, there are no values listed here and therefore the column must hold no data. Service level refers to the level of membership for the website the person holds. The column we wish to predict in this experiment is purchased, since this refers to the event that the customer purchases the service which is being offered. We can also see, by looking at the Has Dependents column, that we have some missing data entries, which is something we'll sort out later on. Onto our experiment now. Just before we start, I'd like to point out that there are times when you may find some discontinuities in this video. This is because the action of running the experiment in this case can take anywhere from a few seconds to half an hour. So for the longer waits, I have sped up the video to keep things moving. So firstly, we need to upload our dataset. Now all sorts of data types can be uploaded onto AML Studio. The full list can be found in the AML Studio online documentation, or just by exploring the options in the user interface. To upload our dataset, we follow New, Dataset, from Local File. Then we browse for our file and select it. It should recognize the type of file and name it accordingly. And the name is editable, and we also have the option to add a short description. I'll describe this as worked example of a customer propensity problem. Then click the tick. We start by locating our dataset in the experiment items pane in the left of our screen. In this case, our dataset is called Propensity Walkthrough Data.csv and is found through Save Datasets, My Datasets. We drag this module onto our experiment canvas like so. We can visualize the data by right-clicking the circular output port at the bottom of the dataset module and clicking Visualize. Clicking on any column brings up various statistics and a graph on the right-hand side. As we established just, the sales channel feature contains no data and is therefore redundant in our dataset. We want to get rid of this. To do this, we need to find Select Columns in Dataset in our Experiment Items pane here on the left. We add this to our canvas and then link the two modules together by clicking and dragging our cursor from the output port of Propensity Walkthrough Data.csv to the input port of Select Columns in Dataset like this. To get rid of our redundant feature, in the Properties pane on the right, we follow Launch Column Selector, with Rules, All Columns, Exclude, Column Names, Sales Channel. To apply our changes, we need to run the experiment. Before this, though, we will save the experiment by clicking Save on the bar at the bottom of the canvas. It is good practice to save work as often as possible when the changes are made, even if autosave is on. Run is also located at the bar at the bottom of the canvas. Okay, so let's click this. Once it has run and we can see the green tick on the right of our module, we can visualize the new results. We can see now that the sales channel feature is no longer there. So we now want to clean our data by removing rows which have any blank values. To do this, we find clean missing data in the experiment items pane, and we drag it onto our canvas. Again, we link these together. Since we want to remove the entire row if it has any blank values, in the cleaning mode drop-down in the Properties pane, we select Remove Entire Row. In this case, we haven't had to alter any of the other properties listed. The default selected columns is all columns which we want. The minimum missing value ratio refers to the minimum number of missing values required for the operation to be performed. Similarly, the maximum missing value ratio refers to the maximum number of missing values that can be present for the operation to be performed. With these properties, we only need one blank value in any given row for it to be deleted. Now, any help needed with any of these modules can be found here in the bottom corner. It provides a short explanation, or, if you follow the link, it takes you to a much more detailed explanation. Okay, let's save and run this. Now, if we visualize using the left output, we see that we have a dataset with no missing values. The Summarize Data module can be used to get a better understanding of the data. For datasets with numerical values, a key benefit of this module is statistical information such as the mean and standard deviation for a column. For datasets which include a lot of categorical variables, like ours, this module can be used to check that the act of cleaning the data didn't alter anything drastically. We'll drag two Summarize Data modules to our canvas, attaching one to the Select Columns in Dataset module and the other to the Clean Missing Data module. This will make it easy to compare the values before and after the removal of rows. Now we save and run. Let me just bring up a second window so we can visualize these modules side by side. Okay, visualizing both summarized data outputs, we can see that all of this descriptive data that this module provides, including things like mean values and measures of dispersion. In our case, we notice that almost all the mean values are extremely similar to what they were before, suggesting that cleaning the data by removing rows didn't significantly alter anything. However, if we look right at the bottom, we can see that the purchased mean has increased significantly. This is a potential problem since this will be our target variable in this experiment. We can see that the mode has changed from 0 to 1, which implies that the clean has taken far many more 0 cases than 1 cases. Now, why is this? At this point, we are prompted to examine the dataset a bit deeper, and it helps to keep in mind the underlying business problem. Looking at the left visualization, we see that the missing value count of 23,970 occurs in many of the variables, which suggests it is highly likely that all of these missing values in their respective variables lie in the same row entries in the original dataset. It is also highly likely that the majority of these row entries lead to an overall purchased class of 0, which represents did not purchase, because it is likely a customer wouldn't go through each stage and fill all their details if they weren't that interested in purchasing the new service. Moreover, these customers would probably fill in as few details as they could. This would explain the increase in mean from the left dataset to the right dataset, since a lot of row entries with the purchased class 0 would have been removed. Now that we have an idea of what could be going on, we should move over to Excel to try and confirm our thoughts. So, opening the dataset in Excel and scrolling through, we can see that our inkling has been confirmed, with all these row entries that only include 2 items of information, with the rest being blank. As expected, they all have the purchased value of 0. Referring back to our hypothesis, we are interested in being able to predict positive, or did purchase, results from customers. Also, our outline for this problem stated that we were basing our predictions on the information provided at various stages throughout the purchasing workflow. Here, though, it is quite apparent that these customers haven't got much further than the initial stage. Therefore, these nigh on blank row entries, which lead to a did not purchase result, are useless to us, and therefore getting rid of all these values in our case would not introduce any significant bias. We are only interested in full row entries to perform our predictions on. We can now carry on without having to worry about the reliability of our future findings. We now want to make all the features categorical to specify that the values in the selected columns should be treated as categories, not as results, scores, labels, or other values. For example, the data in the industry column aren't scores. They just refer to a certain professional industry, for example, automotive or hospitality. Making this change means that the actual data values will not be changed, but machine learning algorithms will handle the data differently. So to do this, we find and add the Edit Metadata module to our canvas. Again, we link up to the leftmost output port of the Clean Missing Data module. In the Properties pane over here, we launch the column selector and select all of the columns. We also click on the Categorical drop-down and choose Make Categorical. There is no need to change any of the other properties. So we save and run this. Now we can see that all features are now categorical. Since purchased is the column we wish to predict, we need to change its field from feature to label. Feature is a machine learning term that refers to the independent variable. Likewise, label is the term for the dependent variable. So changing the purchase variable to a label tells AML that this is the target variable. In other words, this variable will only be used when training or validating our model, but when we are scoring our model, it will be the variable the model is aiming to predict. Our model is effectively trying to replicate the observed data values with a high success rate. We add another Edit Metadata module and link it like so. Through Launch Column Selector, we select the column Purchased. And then in the Fields drop-down, we select Label. Now we save and run. Clicking on Visualize, we see that Purchased is now a label, whilst all the other variables remain as features. We now want to do some prioritizing of the features in the dataset. A good mantra to have in data science is that simpler is often better. The fewer features a model depends on to successfully predict results, the better, as it means the model is more flexible and adaptable to future data patterns. One of the many standout features of AML is its ability to identify the most important data out of a dataset from a scoring method you choose. There are a variety of algorithms provided to do this, and in this step we will use a Pearson correlation as our scoring method. A Pearson correlation calculates the linear relationship between the features in the label, and we want to locate the features with the strongest linear relationship. If it is a perfect positive linear relationship, our score will be 1. Otherwise, we are aiming for values which are as close to 1 as possible. So we will decrease the number of features to include from 13 to 10, and the 10 features it leaves us with will be the 10 features with the strongest linear relationships with the column Purchased. 10 is simply a sensible starting point as it leaves us with a high proportion of our original dataset, whilst getting rid of a few of our least useful features. If we find that this set of features proves successful in developing our model, we could iterate on this step and keep reducing the number of features until it affects the model's performance. Equally, we might find that increasing the number of features is necessary to develop a successful model. We enforce this by adding the module Filter-Based Feature Selection to our canvas and linking it to the previous module. Next, we make sure that the Pearson correlation is the scoring method chosen. Then we launch the column selector and select our target column as Purchased. We finally select the number of desired features to be 10. So, save and run it. Now click on Visualize. So the module has ordered the features in terms of highest predictive power and got rid of the 3 weakest predictors. You probably won't be able to notice which columns exactly it's got rid of by looking at this output, but by visualizing the other output, which has all the values of the correlation between each of the features in the label, we can see that the features that have been discarded are the 3 with the lowest correlation values, which are employment status, is staff member, and age range. We are now approaching the end of our data manipulation, but to run some algorithms on the dataset, we first need to split the data into 2 sets. One dataset will be used for training our model, and the other one to use as data to test the tuned model. We choose the Split Data module and link it to the filter-based feature selection output. In the Properties pane, we will keep Split Rows as the selected mode. We will then alter the fraction of rows in the first output dataset to 0.8, so we have an 80:20 first dataset to second dataset ratio. So we are training the model on 80% of the data and testing it over the remaining 20%. The seed is the number that the random number generator, or the RNG, begins generating its values from to create the separate datasets. Setting a non-zero positive value ensures that we get exactly the same split of data each time we run the experiment when the input data is identical, provided we keep the same seed each time. Setting the seed to 0 tells the RNG to start generating its numbers from a random number determined by the system clock, so there is no way of knowing what number it generated the random numbers from, and therefore you can't replicate it on another workspace even if the experiment was identically set up. We will set the seed to 2 in this experiment. Setting the stratified split to true ensures that the 2 output datasets contain a representative sample of the purchase column, so we'll do this as well. Save and run the experiment. Now we can visualize both of the datasets separately. The first has 80% of the data. And likewise, the second has 20% of the data. Now that our data is cleaned and we have split our data into 2, it is time to select a model, train it, and score it with the test dataset. In this example, we will use a 2-class neural network model with its default properties. A neural network is an information process paradigm that is inspired by the way biological nervous systems process information. Neural networks learn by example to adjust their model depending on the data. Azure Machine Learning provides many pre-built models to use that are categorized according to the type of problem their algorithms are dealing with. As predicting propensity is a binary classification, or a 2-class classification problem, we should look under the classification folder in the list of modules and find any of the models that are named accordingly for 2-class algorithms. For the purposes of this walkthrough, I have chosen this particular model because I knew beforehand that this was the best performing model for this dataset. I used the cross-validation method to arrive at this conclusion. In short, the cross-validation technique looks at your dataset and scores how well the model performs against the dataset using a range of different measurements. It can be used to identify the best model type for the dataset. It is still beneficial to experiment with a few different models to find the one that performs the best for your specific combination of features and the size of your dataset. There are 2 different ways we're going to train this model. The first uses a module called Train Model, and the second uses a module called Tune Model Hyperparameters. Train Model trains the model with the dataset provided using the exact parameter values you input for the model. This is ideal if you know exactly what parameters you'd like to use. However, most of the time you won't know what the best parameter combination is for your model, and this is where Tune Model Hyperparameters comes in. Tune Model Hyperparameters iterates through unique combinations of a set of parameters, searching for the best combination with respect to a measurement metric of your choice. This method often leads to a much improved model. Although this module does take a while to run, the approximate length ultimately depending on how many combinations you ask it to test and the size of your dataset. To do this then, we need to add two class neural network modules, one train model module, and one tune model hyperparameters module. It's important to connect the correct outputs and inputs. If we hover over the outputs and inputs, we can see a short description which should give us an idea of what it's meant to link with. So let's go ahead and connect all of these up. Okay, let's take a look at the neural network and its properties. As mentioned earlier, a neural network learns by example and adjusts itself with respect to the input data. Structurally, a neural network has input nodes connected to output nodes through a series of interconnected layers. These internal layers, known as hidden layers, comprise of sets of nodes which are connected to the previous nodes by edges. These edges have weights attached to them which vary depending on the strength of the relationship with the nodes they are connecting. Once trained, the output is a function which depends on each of the input variables. This is what is used to predict results for new sets of data. For two class labels, if the value of the function is less than or equal to the threshold value, then the output would be 0. If the value of the function is greater than the threshold value, then the output would be 1. Here the threshold is the point that separates positively classed values, i.e. 1, and negatively classed values, i.e. 0. By default on Azure Machine Learning, the threshold is set as 0.5. So using this threshold example of 0.5, if the value that the function returned was less than 0.5, the prediction would be 0, and if the value of the function was greater than 0.5, the prediction would be 1. Let's go through and quickly explain each parameter now. The Create Trainer mode lets you specify how you want the model to be trained. There are two options, single parameter and parameter range. Single parameter takes only the value specified in each of its parameters. It is the option chosen when the best set of parameters is known, and is used in conjunction with the train model module. Parameter range is what needs to be selected to utilize the tune model hyperparameters module, since this brings up ranges of values to produce different combinations of parameters that the module iterates through. The hidden layer specification refers to the architecture of the internal layers. The default is fully connected, which means that any given node is connected to each and every node which lies in the layer before and the layer after. There is also an option to customize the architecture of the neural network using the .NET Sharp language. The number of hidden layers, the number of nodes, and the precise way you want the hidden layers to be connected to each other are just a few of the details that you can use this custom script for. The number of hidden nodes refers to the number of nodes you want in the layers between the input and the output nodes. By default, there is one hidden layer with 100 nodes. One rule of thumb states that the optimum number of hidden nodes lies between the size of the input layer and the size of the output layer. In our case, with 10 inputs and 1 output, the tune model hyperparameters module may therefore select a single figured value for our number of hidden nodes. The learning rate controls the size of weight changes between the steps. The higher the value, the quicker the model will converge. However, it results in a more drastic change in the values of the weights between steps, and this can lead to overshooting of local minima. The number of learning iterations represents the number of iterations of the data performed during learning. The more iterations specified, the greater the chance of overfitting the model to the training set. The initial learning weight's diameter is the parameter that controls the initial weights of each of the input nodes. The momentum is used to handle the fluctuations in weight changes over consecutive iterations. It does this by adding a fraction of the previous weight function to the present one. A high value for the momentum can overshoot the minimum, causing an unstable system. The type of normalizer is where you specify how you want to scale the features in order to standardize them. In other words, we normalize to ensure the features have the same range of values for meaningful comparison and to ensure the model performs correctly. Details of the different types of normalization can be found in the online documentation. The Shuffle Examples checkbox determines whether the cases are shuffled between iterations. Deselecting this option ensures cases are processed in the same order each time the experiment runs. The random number seed is the same principle as earlier, i.e. it is the number that the random number generator begins generating its values from to select one case to the next. Remember, setting the same non-zero seed value allows repeatability across different runs of identical experiments. Finally, the allow unknown categorical levels, when ticked, creates a grouping for unknown categories. So if the test dataset contains categories that are not present in the training dataset, they are mapped to this unknown level. To get a deeper understanding of each of the parameters and what they represent in a complex algorithm like this, it would be best to do some further background reading into neural networks. Okay, so let's start by sorting out the properties of this left-hand side. For this model's properties, we'll leave almost all the default properties untouched. We'll just set the random number seed to 3 to allow repeatability. Keeping this module more or less unchanged will make a good comparison for the two different training modules. For the train model module, we only need to select the label column purchased. Let's head to the right-hand side now. For the tune model hyperparameters module to work how we want, one thing at least needs to be changed. On the model's create trainer mode property, we need to select parameter range. This brings up ranges of values that the module iterates through. Once parameter range is selected, we see a different set of default values pop up. To the default list of values in the learning rate and number of iterations properties, we can add more values of our own if we want. For example, we'll add in a couple of values to refine the combinations. 0.005 here, and 10 here. We could add in extra values to the number of hidden nodes parameter, but leaving it untouched won't harm the module's capabilities. We'll also set the random number seed to 3 for the same reason as earlier. We will change quite a few of the properties for the tune model hyperparameters module. We'll start by keeping the random sweep selected. The next property determines the number of runs the random sweep undergoes, or in other words, how many different combinations it performs. We'll set this to 50. Now we'll set a random seed, say 7, and select the relevant label column. Finally, we will set the measurement metric to the AUC, since the AUC is the metric we're attempting to maximize. Now that we have all of our model training modules set up, we need to add a couple of scoring modules and an evaluation module to test the strength of our models against the test dataset and easily visualize the results. A benefit of the evaluation module is that it allows comparisons of two results, which is perfect in our situation. We add 2 lots of score model modules and 1 evaluate model module, and link them like so. We will now save and run the experiment. I won't keep the video running real time since this step can take around half an hour to run just because of the nature of the tune model hyperparameters module. So let's just cut to the end of the run so we can visualize the results. Straight away we notice a significant difference in the graphs. The graphs we're looking at are called ROC curves. ROC stands for Receiver Operating Characteristic. Just to remind ourselves again, rather than simply returning true or false, a predictive model returns a score between 0 and 1 for each record that it classifies. Deciding at what point a prediction counts as positive, i.e. falling into the target class, depends on the trade-offs between predicting false positives and false negatives for the specific scenario. For example, it may be more beneficial to you to be more confident of the positive values at the expense of making fewer positive predictions. An ROC curve helps with this decision by plotting the performance of the model as this threshold value changes. The area below the ROC curve on such a chart is known as the area under curve, the AUC, and to put it simply, the higher the value, the better. The closer the curve is to a right angle, straight up and then straight across, the better. By picking a different threshold, i.e. moving along the curve, you can see that you can tune the model to produce fewer false positives at the expense of missing true positives, or produce fewer false negatives at the expense of missing true negatives. The AUC metric is particularly useful when selecting a model, as it is the only metric which takes account of variations in the threshold. The other metrics assume that a particular threshold has been used in order to compare different models before tuning them to a particular threshold. The blue line is the graph of the left-hand side and the red line is the graph of the right-hand side. We can see that our first AUC is 0.653, which isn't much better than a random guess, which would be 0.5, whereas the second AUC of 0.759 is better than a 3 in 4 chance. More details of the other metrics can be found in the corresponding notebook provided, but as a quick overview, accuracy is the ratio of correctly predicted observations, precision is the ratio of correct positive observations, recall is the ratio of correctly predicted positive events, and the F1 score is a weighted average of precision and recall. Using the hyperparameter tuning module that selects the best combination of parameters clearly makes a difference in achieving the best results in a model, as it took our desired metric, the AUC, up by more than 10% against the model that used default values. So now we have a model that we're happy with, we can head to the conclusion. The result is that we now have a trained two-class neural network model which can predict customer propensity with a success rate of 75.9%. Which supports our original hypothesis. So our model has proved successful according to the criteria we defined, and we could now explore the options for deploying and consuming the model to make predictions over future customer data. This draws an end to our customer propensity walkthrough. You should now have an idea of some of the capabilities of AML Studio, and hopefully you can now get on with projects of your own. Please do study the corresponding notebook for more detail of the concepts discussed in this video. Thank you for watching.